morning. Welcome back. Hello. Hi. Hello. 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 Are you awake? Hello. I know it's Friday. It's Friday. They're awake. They're just not replying. It's too early on a Friday. It's right before lunch. All of my students want to do nothing but sleep, and I'm going to try to be entertaining today and keep you awake. We're doing two sections today, similar triangles, which is going to feel a lot like similar polygons from last time, and parallel lines with proportional parts. So for this section, we're really going to have to dig way back into, chapter 3, I think, when we did those transversal things. Yeah, I'm getting some coffee cups in my chat right now. Y'all definitely need some coffee. Wake up! All right, let's hop into our first section, section 7.3, similar triangles. We will be solving problems with similar triangles. We're going to identify those postulates and those theorems that can help us out. And we're going to be using proportions. So more fractions. Yay! Everyone's favorites. The sarcasm is real. All right, let's talk first about how we identify similar triangles. So the first way that we have to identify similar triangles is actually a postulate. It's the angle-angle similarity. And what it says is that two angles in one triangle are congruent to two angles in another triangle, then the triangles are going to be similar to each other. This comes from our third angles theorem that said if I have two angles in one triangle congruent to two angles in another triangle, then those triangles are, then the third angle is congruent to each other. And then from last time, when we were working with similar polygons, we noticed that one of the things we had to do to prove that the polygons were similar was to have all of their angles congruent. And so with triangles, because of the special way that they come about and because of that old hinge theorem thing that we talked about before Christmas break, and we were able to compare the length of sides of triangles based on their angle measures, this postulate kind of is almost a natural consequence of that. We're calling it a postulate because I would just want you to take me on my word for it. Don't make me prove it. So we're just going to use this postulate to see if these triangles are similar. So we're going to determine if they're similar. If they are, we're going to write the similarity statement. So let's remind you how to do that with these triangles up here. So I'm going to give them some names. A, B, and C, D, E, and F. Awesome. And our similarity statement is to write the name of the first item, the first figure rather. The order doesn't matter on the letters of these names. Make it spell anything you want. Don't forget your squiggly for the symbol for similarity. We're going to write the symbol for the next triangle. And now the order in which we write the letters of this triangle's name are important. In this first triangle, I wrote the letter A first. In my figure, letter A has one arc. So in my second triangle, I'm going to look for the angle that has one arc in it. And that's F. So F has to be listed first. The second letter in the first triangle's name is B. In my figure, B is the one that has two congruent markings, two arcs. Excuse me. And so D in my other triangle is the angle that has two arcs in it. So D must be listed next, which means E is the one that comes last. All right, we're going to use this postulate 7.1 to prove whether these triangles are similar. As I look at these triangles, I notice right away that L has a measure 57 and so does M. I also notice that one of the letters is missing. So can y'all give me a letter that you want me to name this point here? It can be any letter you want. What was the letter again? D, letter D. Okay. Here we go, letter D. Beautiful. All right. These two are the only angles that I see that are congruent. I know that J is 48 and I know that P is 75. I have no idea what's happening at K and I have no idea what's happening at D. So I think my first step is going to be to figure out what's happening at K. Let's go ahead and find the measure of angle K. Because this is a triangle, I can rely on the triangle angle sum, which says if I add up all of the angles in a triangle, I will get to 180. And so I am going to take 180 and I'm going to subtract off the measures of the angles that I already know. Now, while I write this down and talk, can I get you guys please to do that subtraction for me in your calculators or by hand, whatever is easiest for you, and tell me what is the measure of angle K? You're going to shout it out nice and loud, otherwise type it in the chat. What was your measure for angle K? 75, they told me nice and loud. Thank you very much. All right, K is 75. Yo, hold the phone. Hold up, check it out. Angle P is also 75. That means P and K are congruent to each other. I have two angles congruent in these triangles. That fulfills what I need in postulate 7.1. And so these two triangles are congruent by postulate 7.1. So when asked to explain my reasoning, the strongest reason I can give is to list a postulate, either by code number or by name. It doesn't matter which one. And now I'm going to list my triangle similarity. Oh, excuse me. Maybe I should put my coat back on. I'm getting chilled. All right, L came first. L was pink. Ooh, excuse me. So my second triangle, I'm going to write the pink letter. I then wrote J next. J does not have a color in my second triangle. D did not have a color. And that means that P is last. Not too hard, right? The only way I have of making this hard is either to throw some algebra at you or to give you a figure where there's no numbers at all, like letter B. So let's take a look at letter B. No angle measures, but I need to use the angle-angle similarity, which requires me to know if angles are congruent in order to decide if these triangles are similar. And it seems impossible, but there's some information that this diagram gives me. I'm going to zoom in real tight on this diagram, so it's the only thing that I'm looking at. All right, the first thing I notice is that this line here from R to W, this line is intersecting this line here from X to T. And when lines intersect, they create vertical angles. Right there and right there. Thinking way back, it was like chapter 1, we saw a hint of it. In chapter 2, we saw a hint of it. And we started using it when we got into chapter 4, when we were talking about triangles. And this is this idea that these vertical angles are always congruent. And so I can state right now that angle RSX is congruent to angle WST. Now the question you might be having right now is, why did I make R corresponding to W? The reason I did that is because they lie on the same line. So they're kind of connected and related. All right, I need a reason for this, and my reason that I stated this was the vertical angle theorem. I'm going to abbreviate that as VAT for vertical angle theorem, and you can find that back in chapter 5, or chapter, I think it showed up first in chapter 2. All right, I've got one angle congruent. If I can find another pair of angles congruent, I will have enough for the angle-angle postulate. All right, looking around here, I see this line here parallel to this line over here. And when I have parallel lines intersected by some other line, this line becomes a transversal. If I think way back to chapter 3, when we first talked about transversals, alternate interior angles were congruent to each other. So I have angle R congruent to angle W because of the alternate interior angle theorem. And that showed up way back in chapter 3. I'll do my best to go back and find some cards to add in this section for you so that it links you back to those videos so you can see it, okay? Please remind me. If I don't do it soon, leave a comment in the YouTube video. Oh, hey, I have two pairs of angles congruent. All right, these triangles are similar. All right, triangle RSX, that's the triangle on the left, similar to triangle. Now here in this angle, I said that R and W were corresponding. So since R goes first, W goes first. S and S, and then X and T. Here it is. And asked to explain my reason, here are my reasons. It's because these two things give me postulate 7.1, the angle-angle similarity postulate. Give me your questions. Looking around the room, got no hands, looking at my chat. I got a face and I got some faces, but those were from before. Gonna hydrate. All right, no questions. Let's pop into the homework real quick to see which part of the skill practice this is related to. This is questions 1 through 4. Skill practice 1 through 4. All right. We've got some theorems that can also help us out in determining if triangles are similar. And I know they're going to help me determine if triangles are similar because their conclusions all read, then the triangles are similar. The first one seems really familiar, side, side, side similarity. The side, side, side similarity requires me to find out if the side lengths of triangles are proportional. So I'm looking for side lengths being proportional. So I'm going to take the lengths of the sides, I'm going to turn them into fractions, and I want the fractions to be equal. If I can make that happen, then I can say that they're proportional, and I can use the side, side, side similarity to show that the triangles are proportional, or they're similar. The second one is side angle side. So that's going to feel familiar back from our triangle congruence days. This requires two sides of the triangles to be proportional. The first one, we needed all three sides to be proportional. This one, we only need two. But there is the word and in this. So that's not the only criteria. I also have to look for the included angle being congruent. What does included angle mean again? All right, if I've got some triangles here, so here are my two triangles. If I'm looking at these two sides, we're going to say these two sides are the corresponding sides. And these two sides are also corresponding. Then the included angle is the angle that gets created when those two sides crash into each other. So these two yellow sides in a fraction that is equal to these two green sides in a fraction, and the measure of the angles in between those two sides being equal. Let's apply those to here. I'm going to do A, and I'm going to do 2B. All right, looking at A first. Looking at this, I can use either side, 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 or side angle side. I have all three side measures, so I'm going to see if I can use side similarity to show that these triangles are similar. So I'm going to try to use theorem 7.2. All right, theorem 7.2 asks me to find that all the sides are proportional to each other. So looking at these, I see that this side is going to correspond to this one. And I know it's corresponding to this one because they're, when they cross like this, those opposite sides are corresponding. That was not a good reason. Another reason is if I look at this side right here, 5, it's the smallest number out of these three. And if I look at this one here, 12.5, that's the smallest number out of these three. I think that's the easiest way to think about it. And then these are the medians. All right, I know which side is which. I'm going to go ahead and write my fractions. So I'm going to do the green sides first. I wrote the information for the small triangle on top, the information for the bottom triangle on the bottom. And because I'm feeling the lazy, I'm not going to try to reduce that fraction in my head. Instead, I'm going to use my calculator. When I do 6 divided by 15, I get 0.4. All right, I'm going to do the blue sides. So 8 over 20, that's the small triangle information over the big triangle information. I'm going to divide 8 by 20. And when I do that, I get 0.4. It's looking good. I just need the last pair of sides to show congruent. Going to use some yellow here. Here is the top triangle. Wow, on the projector screen, you cannot see this at all, but I did 5 divided by 12.5. Those of you connected to Zoom, can you tell me if this is reading okay? All right, so it's just the overhead projector that's ugly. Okay. All right, so 5 divided by 12.5 is also 0.4. All three sides create fractions that are equal. That means we have enough to say that they are similar by theorem 7.2, the side theorem. Any questions on that one? Is that okay? All right, let's look at 2B. Okay, 2B. I only have 2 pairs of sides with information, so I can't use side. So I'm going to try using theorem 7.3, which is the side angle side similarity. All right, for side angle side, I need 2 sides proportional and the angle in between those sides congruent. All right, I notice this line and this line intersect, which means this angle and this angle are the included angles. They're vertical angles, and vertical angles are congruent. So these angles here in red, congruent. We've got the angle taken care of. Now let's check the sides. All right, I'm going to write them as fractions. There's the green fraction, that's the triangle on the left divided by the triangle on the right. That's easy to think through, that's 1/2. Now let me do the triangles in blue. Here's the information for the triangle on the left. Here's the information for the triangle on the right. Ooh, that's also 1/2. Yo, the fractions are the same. So my sides are proportional. This is indeed similar by theorem 7.3, the side angle side similarity theorem. Hit me up with questions. Either y'all are still asleep or I'm doing an amazing job. Is the second one? You're like, yeah, sure, whatever, teach. All right, we've got a few more theorems for you. These theorems are really simple. They're just some properties of similarity, and they're really similar to ones we've already looked at. They're the reflexive, symmetric, and transitive properties. It's exactly like the ones of equality, which we talked about back in chapter 1, chapter 2. They're the same as the ones of congruence that we talked about also, I think, in chapter 2. Yep. So reflexive is a thing is similar to itself. Symmetric property is that if you've got a similarity statement, you can reverse the order of your similarity statement and everyone's okay with it. With transitive property, if you've got one thing similar to a second thing, and that second thing is then similar to a third thing, then the first and the third things are similar to each other. Easy enough? All right, let's talk about parts of similar triangles. Now, these two triangles, we have to identify which ones are similar to which. All right, I have, believe it or not, two triangles sitting here. I have the small triangle that is triangle ABD. And I have the bigger triangle, triangle ACD. Now let's talk about whether these triangles are similar or not. They both have A as one of their angles. So by reflexive property, A is congruent to itself. Those two angles are congruent. Now here I have some parallel lines. Thinking back again to our parallel lines and transversals, if I think of, like, say, maybe this line as a transversal, I get this angle and this angle as corresponding angles. And corresponding angles are congruent. So B and C are congruent to each other. I have two angles congruent in these two triangles. These triangles are similar. Phew. All right, now that I know they're similar, let's figure out, whoa, what happened? My screen went black. And we're back. Okay. Screen decided to take a brain break. Don't know why. All right, let's look at BE. Here is segment BE. It has a variable. So if I can find the side that corresponds with that, I can set up a fraction that has this BE information on it. Looking at my triangle name, B and E are the second and third letters. So if I look at the second and third letters from my other triangle, I find that CD is the line that corresponds to BE. This ratio is in proportion. That means it's equal to some other fraction. That fraction is the lines from two other segments in this setup. Now, if I look here at line A to E, there's a variable there. So this isn't helpful right now because I don't know what that measure is yet. So instead, I'm going to look at the line from A to B. A to B is 3. A to B is the first and second letters in the name of this triangle. The first and second letters of the name of the other triangle are A to C. Notice how we have this overlap happening right here. So A to B is 3, A to C is 5. All right, let's fill this in. So we're going to do the small triangle BE, the big triangle CD, the small triangle A to B, and the big triangle A to C. All right, filling all that in, I have x over 3.5 equals 3 over 5. And now this looks exactly like the setup we were doing last time when we were solving proportions. Back when I asked you guys, please show out your work in that cross multiplication. So that's 5 times x. And this one is 3 times 3.5. And if this is super easy for you and you're screaming at your screens right now going, just multiply the 3 and the 3.5 in your calculator and then just divide it by 5. You're not wrong. That's exactly what needs to happen. But I want you to go through the very tedious, the very boring, writing all of this down. So that way, when these proportions get really weird looking at you, Algebra 2, you know exactly what it is you need to do. Questions? Taking a look at our homework, it looks like that is 5 through 8. And then there's a little word problem for you there. I'll let you chew on that. So this is going to be our skill practice 5 through 8. With no questions popping up in chat and everyone falling asleep in the classroom, I mean, not having questions. Let's take a look at the second section. Notes for 7-4. Notes for 7-4, we're talking parallel lines and proportional parts. So we've got basically the exact same sort of triangle setup that we had in the exact previous example. And it leads us to our first theorem. It says, if one line is parallel to one side of the triangle, these two are parallel, and it intersects the other two sides, that's what's happening here at BE, then the line divides the sides into segments of proportional lengths. That is, this piece of that line is proportional to this piece. I can write these two as a fraction, and that fraction will be equal to this piece written in a fraction with this piece. Okay, let's practice that in this triangle setup. Okay, so I'm going to highlight these two pieces are in a fraction together, and these two pieces are in a fraction together. All right, let's read in the word problem and see what information we have for which of those pieces to help us write our proportion. The proportion, again, is two fractions equal to each other. I'm going to highlight the colors. So the green and the red are in a fraction together. And again, the pink and the blue are in the fraction together. The pink and the green are both numerators because they're both kind of the longest portions. And the blue and the red are in the denominator together because they're the shorter portions. Could you have flipped these ratios the other way and written the short pieces on top and the long pieces on the bottom? Yeah, you could have. All right, highlighting. PT right here. I have information for PT. PT is pink. TQ is blue. There's the information for TQ. PS is green. That's what I've been trying to find. That's probably going to be my variable. And SR is red. There's information for SR. Awesome. I know where to fill things in, so I'm going to fill stuff in. I've already done the hard part. Going to take a brain break while I fill these out. I'm just matching colors. There we go. Brain break is over. Time for me to do my cross multiply and solve. Again, you're probably screaming at your screens right now, probably yelling in your head, Miss, just multiply the 7.5 by the 2.5. Why are you drawing all of these crazy things? No, why are you writing the 2.5 and the 7.5? Just multiply them with your cat. Because I want you to get the practice of writing these out and thinking it through this way. Again, I'm trying to set you up for success in Algebra 2, where you have to do this with fractions that just, they look gross. Okay? So please Write this down for yourself so that you'll always see it. And that way, hopefully, when you see this again in Algebra 2, you won't be freaked out. Questions? I saw some shakes of the head. That means that you're awake. Awesome. Very nice. Thank you very much. All right, let's talk about our next theorem. Converse. That means it's the same as the triangle proportionality theorem that we just looked at, but it's going in the opposite direction. If a line intersects two sides and it makes those pieces proportional, then the line is parallel. Notice where this one said, if the lines are parallel, then these pieces are proportional. So this theorem up here you use when you know lines are parallel and you're trying to give a reason why you're calculating the way you are. This theorem gets used when you have things you can calculate with and you're trying to give a reason why these things are parallel. Like in example 2. Example 2, you're being asked to determine, are these lines parallel? It is not enough for you to say they look parallel, therefore they are. Not strong enough. We have information that we can calculate with. We're given EH, we're given HF, we are given DG, and we need to get some information about GF. Miss, you said we were given DG, but there's no number here with DG. You're wrong. You're right. There is no number there, but look, it says DG is. That means that there's an equal sign somewhere. DG is 1/3 the length of GF. I need to be able to write DG and GF as a fraction and EH and HF as a fraction, and I want those fractions to be equal. If they are, then I can say these lines are parallel. Okay, let's write these two as a fraction first. That fraction is 3/9. Okay, well, I don't really know what measurements these are, but I know that this piece is 1/3 of this. So the question is 3 1/3 of 9? Is 3 1/3 of 9? Can I take 3, multiply it to, can I take 1/3 and multiply it to 9 and get 3? This multiplication seems weird, doesn't it? What if I replace the 9 with a fraction, 9/1? That's easier because to multiply fractions, I go straight across. What is 9 times 1? 9. What's 3 times 1? 3. What's 9 divided by 3? They're the same. This tells me that EH is 1/3 of HF. These are identical in nature. That means these sides are in proportion. Give me questions because this was not as straightforward as some of the others. I did a good job or you all fell asleep? And several of you look over at me. Don't call us out, miss. It's Friday. All right. Before I move on, let's take a look here. That's gonna be 3 through 5. So we've given you enough information now to do the first 5 items. Let's figure out how we're going to do the next 5 items, 6 through 10, where we're talking about mid-segments. Now, on one of your quizzes from chapter 6, when we had talked about mid-segment of trapezoid, I believe the question was written with the word median. And I had several of you come up and go, what was median again? And I apologize, I don't think that I stated it outright, that median of a trapezoid is the same as mid-segment of a trapezoid. I kind of left that as an implied, and I apologize for that. A mid-segment connects the midpoints of the sides. Well, a median connects the midpoints of the sides. So mid-segment and medians are the exact same thing. And here we have this comment that this mid-segment theorem that we're about to talk about is very similar to the trapezoid mid-segment theorem. So let's look at how they're related. The trapezoid mid-segment theorem had us take the 2 bases, add them together, and then divide them by 2 to get the length of the mid-segment. In a triangle, we don't have 2 bases. We only have 1 base. So if we only have 1 base, there's nothing here to add it to. We're just going to take that 1 base and cut it in half to get the measure of the mid-segment. The hard part about this is that the figures now look like this, right? So this mid-segment is connected to this base, and this mid-segment is connected to this base. And you've got to use not only this theorem and this formula that we've just given you, but everything that you can remember about how parallel lines interact when they get intersected. Those are transversals, chapter 3. You've got to remember things about quadrilaterals and their angle sums. That's like chapter 6. And all of those different things. Okay, that's what makes this part a little on the tricky side. Now, from this mid-segment theorem, we have some corollaries that fall out of them. A corollary is something that follows logically from some statement. It's like you're carrying this theorem and the corollary just falls out and lands on the ground. And it's like, hi, I'm here. The first corollary talks about the proportional parts of parallel lines, and it says this. If 3 or more parallel lines intersect 2 transversals, they cut the transversal proportionally. What? Lots of words in here. Remember that transversals are just lines that intersect 2 or more other lines. So we have 3 or more parallel lines, 1, 2, 3, and they're intersecting 2 transversals, 1, 2. They're going to cut these proportionally. That means this piece and this piece will form a fraction, and that fraction will be equal to the fraction you get when you write this piece and this piece as a fraction. The second corollary is that we get some congruent parts of parallel lines. From this idea, if one portion of this is congruent, notice these 2 now congruent to each other. If you have this set up 3 parallel lines, two or more transversals, if it's congruent here on one piece, because they're proportional, these two pieces over here will be congruent as well. All right, let's use some algebra to try to make this hard for you. Find X and Y. All right, here's the diagram. I've got 1, 2, 3 parallel lines, and I've got some transversals. Yo, notice I have congruent pieces. Since those are congruent, makes it really easy for you to write an equation for those two to solve for y. Because these are congruent, this corollary we just talked about means that this piece is congruent to this piece. And so our equations are now super easy to write. There's not even any fractions involved here. There's the equation for the blue pieces. They're congruent because the pink pieces are congruent to each other also. And that was marked for us. So here's the equation for the pink pieces. I feel really comfortable that now at this part of the year, you guys can solve these. So I'm going to go ahead and just solve out one of them for you guys. And while I do that, I'm going to open up the floor to any questions. No questions? All right. I had no questions pop up in the chat. I didn't see anyone turn around and look at me. I did not see any hands go up in the air. So I'm going to assume everything is fine and good and happy. Thank you very much for joining us today. Please remember, if you're watching this on YouTube later, leave a like, hit the subscribe. If you're in my class this year and you're watching this after, hit that bell so that way you know when I upload your video and you can go find it. Especially helpful if you're at the house doing some homework, you're stuck, you don't remember how to do it, you can always pop back here to the video and take a look. When you're doing that, please, please, please leave me a comment with a timestamp on those where I put those examples to make it easier for you to find it if you need it later. Thanks again. Have a good one. We'll see y'all later. Bye. Nothing, no response, not even a bye. Ugh, a very weak bye. You guys need to wake up. It's middle of the day on a Friday. Come on. No. People shaking their head at me. No. It's end of the week. You're done. Well, you know what? So's this video. Peace.